Hi, my name is Ollie Jackson. I'm a rising fourth-year undergraduate at the University of California, Santa Cruz, studying astrophysics and mathematical theory and computation. I helped to install the SHIMM instrument on the Nickel telescope and then had the opportunity to present some of our results at the SPIE Optics and Photonics conference in August of 2023. So this is the poster I presented at the SPIE conference, and if you're interested in reading more about our results, you can check out our manuscript number 12-680-68 with the same title, SHIMM as an atmospheric profiler on the Nickel telescope. So the motivation behind this research is that it's really important for astronomers to have real-time information about the atmospheric conditions at their telescope. And to kind of visualize this, this graphic shows an image of the same star over two different nights, the left being from a night with really good atmospheric conditions or good seeing conditions, and the right from a night with poor seeing conditions. And you can see that when there's these higher levels of turbulence, so worse seeing conditions, you're getting this smearing of light around the star. So if you're looking for exoplanets via high contrast imaging, where you're trying to directly take a picture of the exoplanet itself, it's going to be really difficult to find an exoplanet on a night of poor seeing because of this smearing of light. So if astronomers are able to know ahead of time what the seeing conditions are at their telescope, they can use their telescope time more efficiently. Hence, you could switch to looking at a different target where you expect an exoplanet might be orbiting at a slightly larger orbital radius. This is just one really specific example of why it's important for astronomers to know the atmospheric conditions at their telescope site, another application being Q-based observing. The parameter that I've been focusing on so far with our instrument on the Nickel telescope that describes the atmospheric conditions is the Fried parameter, which is a measure of how far a light wave can travel before it becomes distorted by atmospheric turbulence. So the rest of my poster describes how we use our instrument on the Nickel telescope to calculate and estimate this Fried parameter to give us a really good understanding of the on-site seeing conditions. The Shack-Hartman Imaging Motion Monitor, or SHIMM, was originally designed as a low-cost portable atmospheric profiler. And here I describe our implementation of SHIMM onto the Nickel telescope. On the left, you can see a diagram of our physical instrument, which consists of three main components, the first being a flip mirror, which reflects light from the Nickel's optical pathway into our own, so switching from the red path on the diagram to the yellow path. And then in the middle is an achromatic collimating lens that makes sure all of our light is entering into our camera parallel. And then finally we have our Shack-Hartman wavefront sensor, which consists of a CMOS camera, and then in the shaft of the camera we have placed a Shack-Hartman lenslet array. The Shack-Hartman wavefront sensor samples the incoming light wave and then creates multiple smaller subapertures or spot images from which we can estimate the Fried parameter. The Nickel telescope served as a really great test site for SHIMM on a larger, more observationally driven telescope because of the available subaperture size. So our Shack-Hartman lenslet array gives us about 12 spot images or subapertures across, and then because the Nickel telescope is about 1 meter or 40 inches, that means that each subaperture is roughly 8 centimeters. To get an accurate estimate of the Fried parameter, it's important that the subaperture diameter is roughly equal or on the same order of magnitude as our calculated Fried parameter values, and in this case we're expecting that to be between 5 and 15 centimeters. So a subaperture diameter of around 8 centimeters is perfect. Then on the right, you can see our actual instrument installed into the tub of the Nickel telescope in the guider box. In addition to the physical instrument itself, we also utilize a high contrast imaging Python package, which allows us to simulate how a single layer of atmosphere propagates across the telescope aperture, and then also our SHIMM data reduction pipeline. The HCI simulation is essential in our calculation of the Fried parameter. We calculate auto-covariance maps of both our simulated images and our on-sky data as visualized in this graphic here, where the simulated auto-covariance is on the left and then the on-sky auto-covariance is on the right. We then fit the measured or the on-sky covariance with the theoretical or simulated covariance, using the central strip from both of these covariance maps. The equation in the bottom left describes how we get our first estimation of the Fried parameter, where m is the fitted parameter from fitting the measured autocovariance to the theoretical autocovariance. The negative 3/5 power comes from the Kolmogorov model of turbulence, and then the s is our subaperture diameter. This is only a first estimation of the Fried parameter because then we also need to take into account the air mass above our telescope, for which we use the equation in the bottom right. So using the exact time of our observation and as well as the target star that we're using, we can calculate using the PyFM Python library how much air is above the telescope. Then our air mass corrected Freed parameter simply multiplies our first estimation of the Freed parameter by the air mass to that same power of -3/5 from the Kolmogorov power law. Before we tested our instrument on SPIE, we wanted to make sure that the HCI-PI simulation and our data reduction pipeline would work as expected. So we used the HCI-PI simulation to create multiple sets of simulated images using different Freed parameters ranging from about 7.5 centimeters to 25 centimeters, and then we passed those simulated images through our data reduction pipeline to re-estimate and recalculate the Freed parameter. So in this graphic, on the x-axis is the theoretical Freed parameter that we input into our simulation, and then the blue dots on the y-axis indicate the recalculated Freed parameter from our data reduction pipeline. And up to about 18 centimeters, our pipeline reproduces values that are really consistent with what we set in our simulation. For our purposes on the nickel telescope, this is really, really promising and means that we're ready for on-SPIE testing. And these are our first on-SPIE results. So we collected data through the months of May through July, using about the last hour of the night, focusing mostly on the star Deneb. In blue, you can see the histogram and then the estimated probability density function of all of the Freed parameters that we calculated from the nickel telescope. And then in the orange are Freed parameters that were calculated using open loop adaptive optics data from the SHIMM telescope located also at the Lick Observatory. And then in the red line is the mean Freed parameter for the entire Lick Observatory previously determined in a paper from 1997. And all of our values are consistent, which means that our instrument is kind of working as we would expect it to, which is really exciting. Then on the right, in the top, is an image of our first light detected from SHIMM on the nickel, and on the bottom is an image from our HCI-PI simulation of the SHIMM. So SHIMM has the ability not only to calculate the Freed parameter, but also to estimate the coherence time and provide a low-resolution 3-layer turbulence profile. So the next steps in our research are to build out our SHIMM data reduction pipeline to estimate the coherence time and the turbulence profile, and then continue doing on-SPIE testing. We're really excited to have had the opportunity to test out our instrument on the nickel telescope, and really looking forward to continuing the research and seeing what else comes. Thanks for listening.